Tell us all about that.
Yes. So it's the last talk before lunch, so I will do my best not to go over time. So the title of the paper I want to advertise here is Handle with Care, Relational Interpretation of Algebraic Effects and Handlers. My name is Maciej Piróg, and it is a joint work with Dariusz Biernacki, Filip Sieczkowski, and Piotr Polesiuk. So it is another talk about programming with algebraic effects and handlers. And the reason for this is that programming with algebraic effects is becoming more and more popular way of dealing with effectful functional programming. Right? And there are some interesting properties of algebraic effects and handlers. So they provide the programmer with an elegant separation of syntax, of effectful computation and semantics, and they provide more flexibility in programming with multiple different effects at a time. And by more, I mean more than in the monadic case. Moreover, it is closer to algebraic understanding of effects, where we also have operations, not only composition of monadic computations, and importantly, algebraic effects give kind of a very attractive language for doing delimited control. But we are giving the programmer this, as the saying goes, plenty of rope, and we need to make sure that they don't hang themselves. That is, we need to make sure that they don't shoot themselves in the foot doing programming with algebraic effects. And the least we can do is to provide them with some sound and practical reasoning techniques. And this is the goal of our work. So we wanted to come up with techniques that would allow us to prove things like, let's say, contextual equivalence of programs. And in particular, we're interested in this operational relational techniques. So a very important point is that we don't want to talk about the calculus of algebraic effects and handlers, because there are different ways in which you can express them, different calculi, different type systems, different approaches. So actually, I want to note that there is this nice feedback loop, that trying to develop some relational reasoning techniques, we can see which parts or which features of different calculi are more amenable to reason about. So by trying to design reasoning techniques, we can also design a nice calculus. Right? Nice in the sense that it's easier to work with this calculus in the sense of proving properties. All right, so our point of departure is the Dan Leyen's core calculus of Coca presented at POPL last year, because it seems the simplest one that we wanted to talk about. So we had to, maybe not had to, but we extended it a little bit into what we called lambda HL calculus. So it's a call by value lambda calculus with operations and handlers. So it has row-based type and effect system. I will tell you what that is in a moment. It is simply typed in types, but it is polymorphic in effects. It has effect polymorphism. And we add this novel lift construct, which I will talk about in a moment. And so HL in lambda HL stands for H for handlers, L for lifts. Right, so what about some basic constructs? So we have some effects, and effects have names. We usually call them ELF if we mean some effect or single letter names for specific effects. So we add some operations language. For example, mutable state, single mutable cell has two operations, put and get, and each operation has an argument. So put says, the argument of put is the new state, and get returns the current state. And the handler is a construct that interprets the operations. So the most standard way to interpret state looks like this. So you need to interpret get and put, and we interpret the whole thing as a function from the initial state into the final value. And so the handler has two. The clause, each clause for each operation is a definition like of what happens, what's the result of the whole computation, where this variable r stands for the entire context. So this leads to this, I think, rather complicated operational rule for handlers. So it says whenever there's an operation evaluation position at some point, the handler, we need to find the right definition for the right operation, and then we proceed with the body of this clause, but we also allow this body to use this entire context E captured by the handler here. Right? What I want to say here is that this computational rule looks a lot like this delimited control. Okay, so in our calculus we have a type and effect system. So each judgment gives a type of an expression, but also a row of effects. So as I said before, it's easier to use multiple different effects in one computation. So for example, add new effect R, reader, which has one operation ask, which reveals some hidden value, some hidden global value. Then we can write an expression like ask plus get. It has a type int, and the effect is the row containing of R and S, which says this particular expression uses these two effects, reader and state. Right? And then in the type system, we also decorate arrows with rows, which means that whenever this function is called, these effects can be invoked. Right? And also, rows can be open, which means that they can end with a variable, which can be instantiated, creating a bigger row. So we instantiate variables with another rows. And we also have this effect polymorphism, which means we add a big lambda to the calculus. So one example would be big lambda, small lambda f, f applied to unit, and we can give it a type for all a1 to tau. And this alpha says that whatever the effects, whatever the function f, whatever effects the function f has, the whole function will invoke them. Right? So note that there's some effect subtyping. We can give the judgment for any row epsilon, even though the definition doesn't mention any effect of its own. All right. But there is one very important point about reasoning about this kind of algebraic effect. It's parametricity. So let's try to write some clever function using algebraic effects. And we want to do the following trick. We want to, we have a function f, and we want to count how many times it uses its argument. So how can we do that? We say, all right, so we have this f, but we just don't give it g. We give it this extended thing, which says we first invoke an operation tick, and only then we give it this its argument g. And then on the outside we handle these ticks and count how many times this operation tick was involved. That tick is a very simple operation from unit to unit. But because this very dynamic nature of algebraic effects, this function doesn't necessarily behave as we might expect. Why? Because what happens? Look at the type of f. Like the argument is polymorphic in effects, so it can use some effects that we like. A particular argument can use some effects that we don't know about. And if this effect used by the argument is also tick, then this handler will capture also all the ticks that happen in G. That's not what we wanted. Like this handler captured the tick effect in G. So that is why we need to, that's why we added something that we call the lift operator to the language. The lift operator says, I just add an effect to the effect row on the level of types and in the operational semantics. It just says, so this says that now I'm using two different instances of the effect R. And the operation ask on the left-hand side of plus is a different effect than the operation ask on the right-hand side of the plus operator. So given an expression, to handle this expression, I need to put it in two handlers, because I have two effects, R and R, so I need two handlers to handle this expression. So the inner handler handles the ask operation, just like that, but then the outer handler handles the lifted one. Right? So this is the way of managing multiple occurrences of the same effect in the row. Right? So now back to tick. Now we can just put this in this lift construct and say, this handler simply won't handle ticks in this expression because it is guarded by this lift construct. Okay. That was a calculus. So what seems to be difficult in this calculus, like difficult reasoning? So first of all, the control structure in the style of derivative continuations. We have non-termination because the handler can invoke the same effect. So even though the calculus is simply typed in types, it can still be non-terminating. We have this effect polymorphism that we need to take care of. And we have this construct to manage multiple effects in a row. And so what we do is in the paper we built a relational interpretation of our calculus, lambda-HL. And we show some things like contextual approximations, contextual equivalence, as well as type soundness of the calculus. So it uses mostly some recent but standard techniques of reasoning using logical relations. So the two novel things are that we had to take care of is we had to come up with an interpretation of effect rows because we have a type and effect system. And also because we use this technique of bi-orthogonality to build this whole interpretation, we also see that we have to build one more closure. And this is for something called simple expressions. That is because values are not the only reducible expressions. For example, op_v, where op is an operation, is not a value in the calculus, but we cannot reduce it further because op does nothing without the handler around it, or around the evaluation context where op_v is in an evaluation position. So we need like another closure which relates this kind of expressions, but there's some subtlety here. Because we often want to show things like a pure program is equivalent to an effectful one, right? So then we want to relate operations with pure values, for example, or pure expressions. So there are some subtleties here. I think I don't have enough time to explain the definition in more detail. About the non-termination, we use the, I think now, pretty standard technique of step index logical relations. But we hide this, the step index arithmetics by interpreting everything in this category of ordered families of equivalences. Right, so it has a very nice internal logic. Where we have a later modality, we just need to put it in the right places, and then we can find the right fixed point to interpret our logical relation. So, as a side note, this internal logic is not consistent with excluded middle, if you care about such things. All right, so we have a cog formalization of this. So it uses Piotr Polesiuk's X3 library, presented last year on cog workshop here at POPL. So it's very useful for reasoning with step index relations. So it has 4,000 lines of code. I don't think it matters in case of cog formalizations, right? But it's available online. You can download it and have fun with it. And we also have some examples. So I chose 2 examples from the paper. There are more examples in the paper and more complicated examples. But these are the 2 examples that I find interesting. And I also feel good that we formalized these examples. I mean, maybe not formalized, but we formalized the examples, but we also checked it using our machinery. Because these are things that intuitively I think are equivalent, but it's better to check it. So my favorite example is expressing state as a composition of reader and writer. Right? So we have this state effect with 2 operations, put and get, and consider 2 effects: reader, which reveals a value, and writer, which writes a value somewhere. And then we can construct this term, which is the combination of 2 handlers, one for reader, one for writer. And then we use ask as if it was get operation, and tell as if it was a put operation. Right? So how does it work? So whenever you start with some initial state S, and whenever you ask for the current value, just say S. Nothing surprising. But whenever you see tell, which is something like a put operation, what you do is that you exchange the handler for reader. You say, okay, so I will put it in this lift construct to neutralize the old handler, and I will give you a new handler, which just will give you the answer as prime, the new state. Right? So it seems that with some hand waving, you can try to convince yourself that this is really equivalent to the usual way state works, but it's good to have a proof. And another example is that there's something called return clause in handlers, which deals with pure values when there are no operations. And we claim that with our lift construct, you don't really need this return clause. Also seems plausible if you look at the operational semantics, but it's good to have a proof. Things to do next. So the calc is very simple. It doesn't have many base types, for example, when you have unit. We don't have value polymorphism, so we believe that all this is kind of orthogonal to what we did, but it's good to check it, right? We don't have things called shallow handlers, which are also important in practical applications of algebraic effects. And like the most promising direction of future research is look at local definitions of effects to give more modularity, to have effects in a module and do not allow it to leak outside. So it might require something like this Kripke logical relations, but we don't know yet. And to sum up, the part of the paper is a study of a design of a calculus for algebraic effects and handlers. And then we built a logical relation. So in this talk, I focus on the first point. I'm happy to discuss the second point. It's fully formalized in cog, the language, the logical relation, and some examples, including the ones I just shown you. Okay, thank you. That's about it.
Okay, so we have time for a few questions. I'll start it off with our online question from Ohad Kamar. So he asks, how does your modified biorthogonality technique compare to Shinya Katsumata's TT lifting for algebraic operations?
I'm not ready to answer this question. I don't know, really. So, for sure, Shinya doesn't cover handlers, right? If I'm not mistaken. So, in this sense, it's for the here's just operations without handlers. So, but we didn't really look at the differences there, to be honest.
So, any questions out here?
So you said that it looks really like delimited control. So is there any encodings between?
So there's an ICFP paper by Sam Limby, Ohad Kamar, and some other people on comparing these two things. It's last year's ICFP, I guess. So there's a obviously it all depends on the precise definition of your type system. So it's always very subtle what you can encode and what you cannot encode. But they encode some language with algebraic effects in some language with limited control and vice versa.
Any more questions? Okay, then let's get back to you.
Thank you.